Welcome back, AP Stat. This is Bootcamp number 2, free response. These are problems from the 2012 AP Statistics exam. Let's get to work. So for our first question, we see the scatter plot below displays the prices in dollars and quality rating for 14 different sewing machines. Part A, describe the nature of the association between price, the x-axis variable, and quality rating, the y-axis variable, for the sewing machines. Take a moment, try this one on your own, and check your answer by unpausing the video. All right, let's see the answer. The association, we would say, is weak, positive, and looks nonlinear. In general, you want to say whether the association is strong or weak, whether it's positive or negative, and whether it's linear or nonlinear. Additionally, we should note that machines under $500 show no trend. It's a bit chaotic. But more expensive machines show a positive association, which makes the overall association positive, albeit weak. Let's look at Part B. One of the 14 sewing machines substantially affects the appropriateness of using a linear regression model to predict quality rating based on price. Report the approximate price and quality rating of that machine and explain your choice. Pause the video, try B on your own, and then unpause the video when you want to check your solution. All right, here comes the solution. The machine that costs about $2,200 and has a quality rating of 65 affects the appropriateness of the linear model, and that, of course, is this point right here. This value would be significantly below the least squares regression line compared to other data points, since it doesn't follow the trend for machines above $500, where we start really seeing that trend. Okay, let's look at Part C. Chris, hi Chris, is interested in buying one of the 14 sewing machines. He will consider buying only these machines for which there is no other machine that has both higher quality and lower price. On the scatter plot reproduced below, circle all the data points corresponding to the machines that Chris will consider buying. All right, and the scatter plots are the same. There's no difference there. This is not a gotcha. So see if you can do Part C on your own and unpause the video when you want to check your solution. All right, here we go. Here comes Part C. Those 2 points right there would be points for which there is no other machine that has both higher quality and lower price. You can compare those to all the other points, and you will find that it is true. All right, let's look at problem number 2. A charity fundraiser has a spin the pointer game that uses a spinner like the one illustrated in the figure below. A donation of $2 is required to play the game. For each $2 donation, a player spins the pointer once and receives the amount of money indicated on the sector where the point lands on the wheel. The spinner has equal probability of landing in each of the 10 sectors. For Part A, we're going to let X be the net contribution to charity when one person plays the game one time. Complete the table for the probability distribution of X. All right, so part of the table is filled out. See if you can fill out the rest. Pause the video, try it, and unpause when you want to check your answer. All right, here's the answer to Part A. The table would look like this. For the $2 possibility for X, there's a 60% chance of success. For the $1 possibility, there's a 30% chance of success. And negative $8, there is a 10% chance of success. There we go. So now let's look at Part B. What is the expected value of the net contribution to the charity for one play of the game? See if you can solve this one on your own, remembering that formula for expected value. And pause the video, give it a go, unpause when you're done. All right, let's look at Part B. The expected value for the net contribution for one play is the expected value here. It's going to be dollar amount times probability plus dollar amount times probability plus dollar amount times probability. We use our table up here to do this computation, and we get 70 cents. All right, let's look at Part C. The charity would like to receive a net contribution of $500 from this game. What is the fewest number of times this game must be played for the expected value of the net contribution to be at least $500? Use your answer to part B. Try to solve part C. See how you do. All right, let's look at our answer for part C. If we were to divide $500 by 70 cents, we would get 714 and change. All right, so since each play has an expected value of 70 cents, which we found in part B, there would need to be at least 715 plays for the expected net contribution to be at least $500. Whatever this decimal is, it means we got to round up to 715. All right, let's look at part D. Based on last year's event, the charity anticipates that the Spin the Pointer game will be played 1,000 times. The charity would like to know the probability of obtaining a net contribution of at least $500 in 1,000 plays of the game. The mean and standard deviation of the net contribution of the charity in 1,000 plays are $700 and $92.79 respectively. We're going to use the normal distribution to approximate the probability that the charity would obtain a net contribution of at least $500 in 1,000 plays of the game, right? Don't overcomplicate this one, even though it's part D. Might not be as bad as you think. Try this one, unpause the video when you're done. All right, let's look at part D. So since the sample size is very large, that's 1,000, the mean contribution per play is a normally distributed variable, and the sum of the contributions is also normally distributed, okay? So we would just use normal CDF. We would have 500 is our lower boundary, arbitrarily high number. Mean is 700, standard deviation of 92.79, and we have about 98.5% right there. So it's a simple normal CDF problem. All right, let's look at problem number 3. Independent random samples of 500 households were taken from a large metropolitan area in the United States for the years 1950 and 2000. Histograms of household size, that is, number of people in a household, for years are shown below. For part A, we're going to compare the distribution of household size, number of people in the house, in metropolitan areas for the year 1950 and 2000. See if you can give enough information to satisfy part A. All right, let's see it. The median household size is greater in 1950, 5 per household, than in 2000, between 3 and 4 people per household. Both distributions of household size are right skew. And the variation of household size in 1950 is greater than that of 2000. If some of you were thinking to yourselves, wow, that's pretty much a layout of the CUSS model, C-U-S-S, you are onto something. That is the model that you saw in the beginning of the year if you took my class. First, we talk about center. Then we talk about unusual features. There really aren't any. And then we talk about the shape of the data and the spread of the data. That's a good way of doing it. Let's look at part B. A researcher wants to use these data to construct a confidence interval to estimate the change in mean household size in a metropolitan area for the year 1950 to the year 2000. State the conditions for using a two-sample T procedure and explain whether the conditions for inference have been met. So you got to remember those conditions for inference, forming a confidence interval or performing a hypothesis test. See if you can do it with the information that you're given. Okay, let's look at our answer. This is going to be broken up into a couple parts here. That's not the complete answer. For part B, we would say that data come from independent random samples. That's the randomization condition. And it's satisfied because each set of 500 values were chosen from independent random samples. The problem says as much. The next condition is that we sample no more than 10% of the population. This is satisfied because 500 households is, in fact, less than 10% of the households in a large metropolitan area in the U.S. Think Chicago or New York City. That's an easy one. Population is normally distributed or samples are sufficiently large that is 30 or greater. That is the third condition, and this is satisfied because each sample contains 500 households, so the sampling distribution of sample means will fit a normal model even though the data are right skew. Here comes problem number 4. A survey organization conducted telephone interviews in December 2008 in which 1,009 randomly selected adults in the U.S. responded to the following question. At the present time, do you think television commercials are an effective way to promote a new product? Of the 1,009 adults surveyed, 676 responded yes. In December 2007, 622 of the 1,020 randomly selected adults in the U.S. had responded yes to the same question. Do the data provide convincing evidence the proportion of U.S. adults who would respond yes to the question changed from 2007 to 2008? This is a hypothesis test. See if you can complete the hypothesis test, making sure that you state the hypotheses, define variables, make sure that you check off all the conditions, find the test statistic, p-value, and state your conclusion using the context. All right? See if you can do all those things. Pause the video, give it a go. All right, let's see these steps. We're going to let P1 be the proportion of U.S. adults who think TV commercials are effective at promoting a new product, and we're going to let P2 be the proportion of U.S. adults in 2008 who think the same. We're going to perform a two-sample z-test for the difference in population proportions. You must state that to get full credit. Your hypotheses would be null is P1 equals P2, alternative is P1 is not equal to P2. Now it's time to check our conditions. Both samples are independent random samples. Problem says as much. Also, both samples are far less than 10% of all U.S. adults. Finally, we've observed 676 yes answers and 333 no answers from the first sample, as well as 622 yes answers and 398 no answers from the second sample. All those are greater than 10. We're good to go. The p-value we would get if we used a proper test that would be 2-prop z-test would be 0.0048, and the z-test statistic would be 2.82. So since the p-value is low, we reject the null hypothesis. The data provide convincing evidence that the proportion of adults in the U.S. who respond yes to the question changed from 2007 to 2008. Here comes problem number 5. A recent report stated that less than 35% of adult residents in a certain city will be able to pass a physical fitness test. Consequently, the city's recreation department is trying to convince the city council to fund more physical fitness programs. The council is facing budget constraints and is skeptical of the report. The council will fund more physical fitness programs only if the recreation department can provide convincing evidence that the report is true. The recreation department plans to collect from a sample of 185 adult residents in the city. A test of significance will be conducted at the significance level alpha equals 0.05 for the following hypotheses. Null hypothesis, p equals 0.35. Alternative hypothesis, p is less than 0.35, where p is the proportion of adult residents in the city who are able to pass a physical fitness test. Part A. Describe what a type 2 error would be in the context of the study and describe the consequence of making this type of error. Think about what would constitute type 2 error and what the consequence of that would be. See if you can come up with an answer. Unpause the video when you're done. All right, let's look at part A. Type 2 error would mean failing to reject the null hypothesis that 35% of adults in the city are able to pass the test when really less than 30% are able to pass. So type 2 error always means the alternative hypothesis is correct, but we fail to reject the null. The consequence would be that the council wouldn't fund the program and that the city would continue to have a lower proportion of physically fit residents than the council wants. Okay, now let's look at part B. The recreation department recruits 185 adult residents who volunteer to take a physical fitness test. The test is passed by 77 of the 185 volunteers, resulting in a p-value of 0.97. That sends a clear message for the hypotheses stated above. If it was reasonable to conduct a test of significance for the hypotheses stated above using the data collected from the 185 volunteers, that is, if all the conditions check out, what would the p-value of 0.97 lead you to conclude? All right, don't overthink this one. See if you can come up with an answer and unpause the video when you are done. Okay, here we go. A p-value of 0.97 is high. Forget about alpha equals 0.05. 0.97 is high regardless of what alpha is. So we failed to reject the null hypothesis. There is not convincing evidence that the proportion of adult residents in the city who are able to pass the physical fitness test is less than 35%. We do not have evidence to reject the null hypothesis. Let's look at C. Describe the primary flaw in the study described in Part B and explain why it is a concern. Good stats students will notice that Part B had something a little fishy going on. See if you can figure out what it is, describe it, explain why it's a concern. All right, let's see Part C. This sample is not randomly selected. It consists of 185 volunteers. People volunteering to take a physical fitness test would likely tend to be more physically fit than the population of the city as a whole. If you're not very physically fit, why would you want to take a physical fitness test? Not my idea of a good time. If this were so, the sample proportion would be an overestimate of the true proportion of physically fit people in the city. And now on to the investigative task, everyone's favorite. Two students at a large high school, Peter and Renia, wanted to estimate mu, the mean number of soft drinks that a student at their school consumes in a week. A complete roster of the names and genders for the 2,000 students at the school was available. Peter selected a simple random sample of 100 students. Renia, knowing that 60% of the students are female, selected a simple random sample of 60 females and an independent simple random sample of 40 males. Both asked all of the students in their sample how many soft drinks they typically consume in a week. Parts A, B, and C on this page are divided by lines because the text kind of crashes because of the limitations of my slideshow. So let's look at Part A. Describe a method Peter could have used to select a simple random sample of 100 students from the school. Again, do not overthink this one. See if you have an answer. It's probably going to be frighteningly similar to answers you've given to the same question proposed at many points in this school year. All right, let's see the answer to Part A. Assign each student a number from 1 to 2,000. Using a random number generator, select 100 numbers at random without replacement and sample those students. Pretty easy, right? Now let's look at Part B. Peter and Renia, I'm starting here, conducted their studies as described. Peter used the sample mean x bar as a point estimator for mu. Makes sense. Renia used x bar overall is equal to 60% x bar female plus 40% x bar male as a point estimator for mu. Remember, Renia conducted a stratified sample, okay, where x bar female is the mean of the sample of 60 females and x bar male is the mean of the sample of 40 males. Summary statistics for Peter's data are shown in the table below. Okay, so here's our table. Based on the summary statistics, calculate the estimated standard deviation of the sampling distribution, sometimes called the standard error, for Peter's point estimator x bar. Okay, a sampling distribution for the sample mean, and we want to find the standard deviation of it, right? This question is commonly mistaken, all right? So let's see if you can get it. All right, let's look at Part B. The estimated standard deviation of the sampling distribution is Sampling distribution for sample means the standard deviation is standard deviation of my sample divided by the square root of the sample size, which is equal to standard deviation 4.13 divided by 10, the square root of 100, is equal to 0.413. All right, now let's look at part C. Summary stats for Rania's data are shown in the table below. Here we go, divided between female and male. Based on the summary stats, calculate the estimated standard deviation of the sampling distribution of Rania's point estimator. The overall mean is equal to 60% of the female mean plus 40% of male mean. All right, so we're going to find the estimated standard deviation for this sampling distribution. See if you can find it on your own. Give it a go. Unpause the video when you're done. All right, here we go. First, you don't need to write this down. You wouldn't have needed to write this down, but just a heads up, the standard deviation of the sum of random variables is the square root of the sum of the squares of the standard deviations. You may have learned that the variance of a sum is equal to the sum of the variances. If you were to make that into standard deviations, it would look like this. If you're one of my students, you've seen this formula many times. Also, given a constant a, standard deviation of a times x equals a times standard deviation of x, assuming a is positive. All right, so the standard deviation of 60% x bar female plus 40% x bar male, oops, missing a parenthesis, is equal to substitute into this formula, okay? And if we were to do that, we would be saying standard deviation of 0.6 times x bar female is 0.6 times standard deviation of x bar female, but we still got to square it, so we need to square the 0.6 and the standard deviation. Same exact process applies for the men. We would use this property right here again, take out that 0.4 times standard deviation of x bar male, still got to square the whole thing. Substituting some values, we have 0.6 times 1.8 times the square root of 60. Again, the sampling distribution for the sample mean is going to involve the standard deviation for that sample divided by the square root of the sample size. 0.4 times 2.22, that's my other standard deviation divided by the sample size. Square both of these, sum them, square root the whole kit and caboodle, and you have 0.198. And last but not least, part D. We have a dot plot of Peter's sample data given below, and we have dot plots for the females and the males for Rania's data. Part D. Using the dot plots above, explain why Rania's point estimator has a smaller estimated standard deviation than the estimated standard deviation of Peter's point estimator. All right, here we go. Rania's point estimator has a smaller estimated standard deviation than Peter's because Rania sampled males and females separately, whereas Peter sampled from high school students in general. Since the means of the distributions of males and females are quite different, and the variation with each gender is smaller than that of students in general, sampling each gender separately reduces sampling variability. So Rania's technique was good because it reduced sampling variability via stratification in her sampling.